In this video, I'm going to go through how you can use some things we picked up over the last couple of pre-cal courses to help us to evaluate some intervals that involve trigonometry. So I just want to start with kind of an example to show you where things can go differently. If we looked at this question that we have in front of us, the interval of sine x cos cubed x dx, what I would probably do is recognize that I have the pattern here, u to a power, right? So I've got u to the power of 3. The derivative of cos is negative sign, so I almost have that. So if I was doing this question, I'd probably just go cos x to the power of 3, put my sine x beside it. Say I need a negative for to have u to a power du, a negative here, a negative out here to offset that. And then you have the pattern u to some exponent with du multiplied beside it, which is chain rule. So to undo that, you add 1 to the exponent and you divide by the new exponent, and I would get negative 1/4 cosine to the 4th x plus c. And if you have questions, say, oh, I don't know, did you do that right? Let's check it real quick. Let's take the derivative of this. So the derivative will be done using the chain rule. So it'd be negative 4/4 cosine x would subtract 1 off your exponent. The derivative of cos would be negative sine x. 4/4 is 1. This negative would get rid of this, and I'd be left with cos cubed x sine x, which is the original question. So what I did here is correct. Now, if we were in a classroom setting, I would have normally just put that up on the smartboard and let you folks kind of plug away and see what you come up with, if you come up with something at all. I'm just going to then uncover this, and what I would usually have said, so did any of you get this? So their final answer, if you look at this strategy, is way over here. There's their final answer, which of course looks very different from what I had over here. However, this would also be correct. Now, if you just have a quick look and say, well, what did they do different? What they did different is they involved a trig identity. So with questions with integration, I've kind of alluded to it in passing. Sometimes I might get one answer. You may get another answer that looks somewhat different, and they could both actually be correct. So this student, or whoever went through this approach, what they did is they split apart cos cubed x, and they made it cos squared times cos. And you say, what do you mean they made it cos squared? Well, cos squared x, if you can recall from 12a, that's a trig identity. Cos squared x is equal to 1 subtract sine squared of x. Then they just took these two here, and multiplied them by 1. Actually, it looks like they did a u substitution here. I think they skipped a bunch of the steps here, but moral of the story is, based on the fact that they went through and used a trig identity different than what I did, our answers look different, but they're both correct. Now, in this one, they really didn't have to do this. I would make a pretty good argument for they really overcomplicated the question versus doing it this way. However, many of the questions you're going to run into involving trig ratios, you're going to have to get into unraveling them somehow using trig identities. So the first thing I'm going to do is just refresh your minds. So if you don't remember your trig identities, you're going to certainly want to have them somewhere close by so you can refer to them. You have your Pythagorean trig identities, which are these three here. You have your quotient trig identities, which are these two here. You have your sum and difference trig identities, which would be these ones here. And they don't get used that often. These ones a lot, these ones a lot, and these ones here, again, somewhat. You need to make sure you know these ones as well. These ones are called your double angle identities. So we're just going to, from time to time, throw one of these identities in there to try and help us get pointed in the right direction with an interval involving a trig ratio. So there's no real strategy per se, other than I know my trig identities, and I realize that when I'm facing in the original question, I can't integrate, so I try and shake it up and twist it around by putting some trig identities in and see if that helps. And again, it's like some of the other things we've done. This is like a puzzle. The first thing you might try may not work. I may start into an example here today, and what I try doesn't work. So we have to be patient and realize it's a process in problem solving. Okay, so we're going to start looking at a few of these. This is just throwing these identities out, but a couple of really common trig identities you're going to run into are trying to find the integral of sine squared x dx or cos squared x dx. Both would be done using the same strategy. As soon as I see, now again, this is just if it's sitting there by itself, nothing else. If I have the integral of sine squared x dx or the integral of cos squared dx, my brain is going to hopefully right away say double angle identities. Now again, your brain's not going to say that right now because you don't have any experience doing these whatsoever. With practice, this will hopefully come. So what I know is that the cosine of twice x, there's three options for it. If I just go back here one slide for one quick second, cos of 2x, I'm just using x instead of theta, could be this one, or it could be this one. Well, I want to use the one that involves just the trig ratio I'm trying to integrate. So the one we're doing is the integral, I believe, of sine squared. So I'm going to use this version. Cos 2x is 1 minus sine x squared. Sine squared x. Right? Okay, so cos 2x is 1 minus twice the sine of x squared. And what we're going to do is we're going to rearrange this to get sine squared isolated. So I'm going to, let's say I'm going to bring this over here. 2 sine squared x will go here. 1 subtract cos 2x will go here. Divide by 2. Just put that whole thing over 2. And I'm going to put this expression in here instead of sine squared. So I'm going to replace sine squared with this. 1 minus cos 2x. Now it's over 2. That would be the same thing as just putting 1/2 out here, like so. Well, I now have the integral of two separate terms. First one's really easy. I can do the integral of 1. It's just simply x. This one, the integral of cos u, is one of my differentiation rules now. And the only thing missing is the du, which is only a constant 2. So essentially what I've got now are two separate questions. 1/2 integral of 1 dx minus 1/2 integral of cosine 2x times dx. Well, for this to be one of our differentiation rules, it needs to be cos u du. So I need to put a 2 there, which means I need to put a 1/2 out there. Now, when we continue with our solution, the integral here of 1 dx is just x, so I get 1/2 of x. Cosine u du, that's the derivative of sine u. So I'm going to have 1/4 sine of 2x plus some constant c. You may check an answer key, let's say, and look and say, oh, I don't see that. And for whatever reason, you'll see this instead, minus 1/4. Sorry, let me fix that. Be minus 1/2. Minus 1/2 sine x cos x plus c. And sometimes students who don't have a good grasp of their trig identities will say, what the heck just happened there? Or why do they get sine and cosine in there? All they did is put the double angle identity in for sine 2 theta, which says the sine of 2x is twice sine x cos x. So imagine if I put that in there instead of this, well, you'd have 2 over 4. That's why it went to 1/2. And then you'd be left with sine x cos x plus c. And there are situations we'll run into later on where it's definitely to your advantage to switch into this. And the only difference, if you notice, is your angle or your argument here in this line is referring to the angle 2x, whereas down here you're now referring to the angle x, which in some questions, again, eventually, that may be something you'd want to have happen. Okay, so in that one, I would mark either that one or that one. They'd both be right. But that's what you, so if you see the integral of sine squared x dx or cos squared x dx, you're going to go to double angle identities. Now you say, well, how would it be different if it was cos squared? Let's just think about it for a second. If it was cos squared, we'd go with this version. It's 2 cos squared x minus 1. And then when I rearrange, it would be cos 2x plus 1 equals 2 cos squared x. And then we divide by 2, and we put this in there instead of cos squared. All right, so that's the first one on your radar. The integral of sine squared x or the integral of cos squared x, that is the strategy you're going to use to get through those ones. It's a really common one you'll run into, so please make sure you make yourself familiar with that strategy, and hopefully it all makes sense to you. All right, on to my next example. Let's see what I'm dealing with. So this one, I think what I would probably do here is put in a quotient identity for this one. And as I said earlier, it's like a puzzle. Maybe I do that and it doesn't work, and I'd start over and try something different, because there's options for cos squared. I could be putting 1 minus sine squared in, but what I don't like is I'm kind of leaning towards maybe some kind of a chain rule where I want a trig function with its derivative beside it. Well, tangent's derivative is secant squared. Cosine's derivative is sine. So I'm thinking that if I switch this out and make it sine x over cos x, and I leave this, simplify that, well, that cosine is going to get rid of one of those, and we're down to this new question now, the integral of sine x cos x dx. And hopefully you now notice, oh, this is going to be good because I've got u to the 1 with du sitting right next to it. Chain rule. So the antiderivative of this would be u squared over 2 sine squared x over 2 plus c. Right, because I had u to the 1. This was du. So to undo that or integrate that, I add 1 to the exponent and I divide by the new exponent. And the derivative of sine was exactly cosine, so I didn't have any constants to play around with. I wasn't missing any negatives. It was perfect. So you would be finished. So that one I used a quotient identity. Now, that one wouldn't be one that I'd say, well, memorize that pattern. This one, definitely be aware of how to deal with integral of sine squared or cos squared by itself. These ones over here, where you start throwing multiple trig ratios on the go, it's just a matter of playing around with a trig identity and trying to find the right one that'll help you get out of the current situation where it doesn't integrate. All right, let's have a look at this one. Well, if I was checking my rules of differentiation for trig functions, tan squared is not one of my rules. There's nothing I take the derivative of that gives me tangent squared. However, I do know that from my trig identities, just back up the page here for you, tangent squared plus 1 is secant squared. So I could replace tangent squared with secant squared minus 1. Well, I'll go back and see, you say, well, that really helped if I did that. Tangent squared of an angle plus 1 is equal to secant squared of an angle. So if I move that over there and said secant squared theta minus 1 is going to go in instead of that, would that be to my advantage? Well, remember, you're going to take the integral of whatever you put in there. So it's going to be the integral of this binomial. Would you prefer to have a secant squared there instead of tan squared? Of course, your answer is going to be yes, because you know that the derivative of tangent theta is secant squared theta. So if you have secant squared theta and you want to take its integral, you can tell me it's tan of theta, right? Because integrals are just derivatives in the opposite direction. So I think we definitely would want to just swap this out to secant squared theta minus 1 dx. Then it becomes the integral of secant squared theta d, what do I got here? X, sorry. Secant squared x dx minus the integral of dx. This one is tangent x, and this one would just be minus x plus c. So again, trig identities played a role in here. Continuing on. Well, this one, sines and cosines on the go, which is a decent scenario to have. One of the things that you kind of watch for in these types of ones, especially when you got just sines and cosines, no addition, subtraction or mixed in there. So whether it was a quotient or a multiplication, I'd kind of watch for the one that has the odd exponent on it. And for the lack of a better term, this isn't one that I've used, but I've heard lots of other instructors, and so I've kind of borrowed it from them. It's called peeling off a ratio. So what we're going to do is peel off one of these, and you'll see why in a second. So I'm going to leave it as sine to the fourth x over cos squared x. I'm going to peel one of those off. Now, the reason you do that is because you want that ratio that you peel off to serve as du. And you're going to try and turn the other stuff that's left over into something that you can chain roll with sine x being du. Well, sine x is the derivative of cos x. Close anyway, we're off by a negative, but it's okay. Derivative of cos is negative sine x. So that tells me that I don't mind this one down here, because that's really just cos to the negative 2x. You could jump it up here and it would be a chain rule. I don't like this sine because the derivative of sine is not sine. So what you're going to do is use a trig identity. Well, another way to write sine to the fourth is sine squared x squared. The denominator is cos squared x. I still have my sine x dx out here, which is hopefully at some point going to serve as my du for some chain rule. Okay, so here is now where a trig identity will come into play. Sine squared x. Hopefully you quickly recognize that you could replace that with 1 subtract cos squared. So we are going to take the original question, replace sine squared with 1 minus cos squared. Still have your cos squared down here. Now you still have your sine x dx out here. Well, we're going to clean up all this mess and this fraction and see where it takes us. So it's the integral. Square this binomial, so square the first, multiply and double, square the last one, all of that, over cos squared x, and I still will have my sine x dx here with us. Now, this fraction, rational expression, so I've got a trinomial here, all over this monomial. Well, that just simply means that each of these are going to divide by cos squared. 1 over cos squared is cos to the negative 2 of x, minus cos squared over cos squared cancels. Cos to the fourth over cos squared would be a positive cosine squared of x. sine x dx, still sitting out here. So this is starting to look a little bit better. What you're now going to do is recognize that if you multiplied sine x dx by each one of these three terms, you would generate three separate questions that you could fairly easily get the integral for. So what we're going to do is distribute the sine of x in there now. And we've got cos x, I'm going to write it this way. So there's u to a power. It's now got du sitting right next to it. Minus 2 times sine x. That's an easy antiderivative. Plus cosine of x squared. That's cos squared x. Multiply that by sine of x. And then you've got your dx. So all I've done is distribute sine of x to each one of those. And what it has done is it has set up u to a power du. U to a power du. And this is just a straight anti-differentiation rule. So if I split these all up now, what I end up with is the integral of cos x to the minus 2 times sine x dx minus 2, the integral of sine x dx plus the integral of cosine of x squared sine x dx. Now we're going to anti-differentiate or integrate each of these three, and we're going to get, add one to your exponent. Oh, wait a second. No, get it. So cos u, the derivative should be negative, so I need to put negative there, negative there, negative there, positive there, negative there. Now switch that to a negative. Okay, so now let's try that again. Now I've got u to a power du. So I'm going to add 1 to the exponent, which will make it negative 1. Divide by negative 1. So remember, we generated a negative out here because of this. Well, now the negative 1, when we divide by, it's going to switch it back to positive. So you're going to get cosine x to the minus 1. I find a lot of times students get to here, which is outstanding. They really know what they're doing. And then you got to really, really pay attention to your negatives in this last line. So students wind up with the wrong signs in front of me. So you got to be very careful here. Negative sine x is the integral of cos. I got a plus here, so I'm not going to do anything other than put plus 2 cos x. Now my exponent's positive this time, so when I add 1 to the exponent, it's going to go to 3. Remember, this became a negative because of that negative. So it's going to be negative 1/3 cosine cubed x plus c. So I think you can agree that that one, certainly, if we look at the whole body of work we had to do here, yeah, that one got a little bit more complicated. And unfortunately, that's kind of the level at which we've got to be able to manage these types of integrals. That would be considered a fairly challenging integral. I think it's pretty obvious from that. Okay, so let's go to the next. I've got a few more here. If I look at this next one, all right, here's the next one. This is another one of those ones I've compared to like the integral of sine squared and the integral of cos squared. When you run into it, you've got to pick it out and say, oh yes, this is that one we have a little trick for. Again, if we were doing it in class, I'd kind of try and let you guys uncover yourselves. But without that option right now, we're just going to kind of, here are the hints I would have given students. I'd say this is the answer. And then maybe that might lead some of you to figure out what the little trick is. And then my hint number 2 is I would tell students it is always legal to multiply by 1. Of course, oh yeah, sure it is. Well, here's the trick to this one. The integral of secant x is found by multiplying by something that's equal to 1 that generates this as its answer. To get ln of something, you must have ended up with du over u. So I want the numerator to end up being the derivative of the denominator. So to do that, all I got to do is multiply by the secant of x plus the tangent of x. Whatever you multiply the numerator by, you'd have to multiply the denominator by the same thing. Sometimes students say there is no denominator. Well, there always is. There's always a 1 there. And you have your dx out here. Now watch what happens. Integral of secant times secant. Now just think of differentiation rules. What is secant squared x the derivative of? The answer is tan x. Look at that. That's it down here in the bottom. Then you multiply the secant by this, and you get secant x tan x. Hopefully you recognize, hey, that's another differentiation rule. That's the derivative of secant x. Look at that. That's sitting down here. Now I'm just going to change the order of these so you can kind of see how everything lines up better. I'm just going to write the bottom as tan x plus secant x. If you looked at this derivative of the denominator, I said, what's the derivative of the denominator? You'd say the derivative of tangent is secant squared x plus the derivative of secant is secant x tan x. The numerator is exactly, perfectly the derivative of the denominator. And if you have the integral of du over u, it is the natural log of u. So I've set up the pattern for natural log. Therefore, my integral will be natural log. Notice I'm going to go with the absolute bars. We had a chance to talk about that at some point when we did antiderivatives, because you can't take the natural log of negative arguments. So this is just to guarantee that that turns out to be positive, plus c. It's pretty much the same strategy if it's cosecant. I should throw it on a blank slide here. If I have the integral of cosecant x dx, well, my strategy, I'm not going to multiply by secant this time. Hopefully you're thinking cosecant. Cosecant in your derivative rules, the derivative of cosecant of u is negative cosecant u cotangent u, and the derivative of cotangent u is negative cosecant squared u du. So much like tangent and cotangent kind of pair up in a lot of these properties, whether it's trig identities or derivative rules, cosecant and cotangent are often working together in these rules and identities. So here, what I would do is multiply by not cosine plus, sorry, not secant plus tan. This time I'd multiply by cosecant x plus cotan x. But this one will have one little extra trick to it, which we'll see here in a second. So I might still have my dx here. And remember, this is completely legal because it's really nothing more than a fancy number 1, which you're always allowed to do, multiply by something that's equal to 1. So the numerator becomes the integral of cosecant squared x plus cosecant x cotangent x over, again, I'm just going to switch these, cotan x here plus cosecant x here. So in this one, it's all not quite as nice as the last one, but because the numerator is not exactly the derivative of the denominator, but the only thing missing are negatives. So if you were to take this whole numerator and multiply by -1, that would give you negative this, which would be the derivative of this. That would give you negative this, which would be the derivative of this. So if you multiply by a negative there, you got to multiply by a negative up there. And now you have a negative natural log cotan x plus cosecant x plus c. So that's the only little bit extra step at the end, is the numerator is not quite the derivative of the denominator. It's off by a factor of -1. Multiply by your -1, offset it with a -1 in front, and then you're in business. All right, so those are two trickier ones you got to watch for. All right, now this is one of the more difficult integrals you would ever run into with trig functions. It's the integral of secant cubed x dx. This is one that I found for years and years, even myself, from one year to the next, because you don't run into it too often. I eventually made this slide so it would remind me of the strategy that I would use to integrate this type of question. So their description they use is, how do you integrate secant cubed x dx? It says by trickery. So this is a kind of a neat little trick they do here. They basically turn it into integration by parts. So if you look here, they split this up and they split it. I'm going to do it all out here in a second. This is again from a textbook somewhere, but it's not. It's just to remind me the strategy. So I'm going to split it into the integral of secant x, secant squared x dx. And then I'm going to let u equal secant x, and I'm going to let bv equal secant squared x. So let's give ourselves a clean page here. And imagine we had to do the integral of secant cubed x dx. So we're going to split it. Secant x, secant squared x dx. So the reason I split it that way is so that this is now the derivative of tan, so it can be my dv. So I'm doing integration by parts like we did in our last video. So u equals secant x, dv is secant squared x dx. du is secant x tan x, and v is tan x. Got the dx on this one. All right, so the integral of secant cubed x dx would be uv secant x tan x minus the integral of v du, which is secant x tan x times another tan x dx. So there's your v times du. Well, let's just see what we're dealing with here. So I've got integral of secant cubed x dx equals secant x tangent of x minus the integral of secant x tangent squared x dx. So then my question is, well, is this integral any better than this? At first glance, it really doesn't appear to be, but if we know, this is kind of where the trickery comes involved. From experience, we have found out that if we replace tan squared, so tan squared of an angle is equal to secant squared x minus 1, because 1 plus tan squared is secant squared. So I'm going to replace that with secant squared x minus 1. And there's a reason I wrote the original question here. This is similar to a strategy I showed you in the last video. Secant x tan x minus the integral. Replace this with secant squared x minus 1, trig identity. Dx. Now I'm going to expand this into here. Some of you maybe already see where this is going. Secant cubed x dx equals secant x tan x minus the integral of secant cubed x minus secant x dx. Well, if I split this integral, I have left here, so if I split this into two, do you notice that one of the integrals is going to be the original question? It's going to have a negative in front of it. I don't know if you can remember the one we did by parts with the e to the x's. It looked like it was going in a circle, and then we move that integral over and collect it with that. That's where we're going with this one. So we're going to go integral secant cubed x dx equals secant x tangent x minus the integral of secant cubed x minus minus, so plus the integral of secant x dx. This integral right here, we should not be afraid of at all because we just went through the little trick how to do that. So I can do this. Well, if I just take this one and move it over here, it'll group it with this one, and we will get 2 integral secant cubed x dx equals secant x tan x minus, so we know how to do this one. Remember, it's multiplied by secant x plus tan x. That turns into the natural log. I'm not going to go through all the whole process this time because we know what it is now. So the integral of that would be replaced with natural log of secant x plus tan of x. Absolute bars. Almost there. So then to get the integral, the original question, I just divide both sides by 2. Take half of that, take half of that. The integral, which is what I'm trying to figure out, of secant cubed x dx would be 1/2 secant x tan x minus 1/2 natural log secant x plus tan of x, also constant. See, so that is a neat little trick. So there's a question the first time students run into it, they would often have a lot of difficulty. However, after having a chance to see it, it's supposed to now trigger and say, oh, okay, I remember doing that type of thing. So that if we ran into the integral of cosecant squared, cubed, if I had the integral of cosecant cubed x dx, it's not exactly the same as the one we just did, but hopefully it would trigger your brain to say, hey, I remember doing one like this before, except the ratio was secant. And what I did is I separated it into these, my x, and then away you go, you do the same thing. Let u equal cosecant x, let dv equal cosecant squared x dx. Now the only thing that happens with cosecants, as you know, I'm not going to go through the whole thing, but you got to watch your negatives because this is missing a negative, blah, 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 all that stuff. But essentially, it's the exact same strategy. Just switching the pattern or the pathway is the same. It's just you're using cosecant and cosecant squared rather than secant and secant squared. Okay. So I just got 3, how am I doing for time? So I got 3 quick intervals here involving trig functions. Let's see what we can do with each of these 3. So this first one, remember I mentioned one time about the odd exponent? I'm going to separate this one and I'm going to peel off a trig function. I'm going to peel off one of my sine x's. I'm doing that for this to serve as the du. Well, if this is du, I need cosines. However, if you know your trig identities, there's a way to switch sine squared into 1 minus cos squared. So it's 1 minus cos squared goes in there instead of sine squared. You've got your sine x here beside it, dx. Distribute that into each of these. You're going to get 2 separate intervals. The integral of sine x dx minus the integral of cos x. I'll write it this way just so we can kind of see our chain rule better. So now this is easy. That's just the derivative of negative cos. So it'll be negative cos of x. Now this one I need a negative for the chain rule, which will switch that to a plus. Add 1 to your exponent and divide by your new exponent. 1/3 cos cubed x plus c. Now let's go. Let's get this guy out of the way. Just putting them on a new page here afterwards. We have room. All right, we'll come back to that guy in a second. All right, let's see. Tangent to the 4th x dx. My original gut feeling is saying to split this. Now, I'm not peeling one off. I'm going to split it into tan squared x, tan squared x dx. And unfortunately, there's no quick, easy way for me to say, oh, well, you do it because this. Unfortunately, you end up seeing examples and you get experience and practice doing these, and it just kind of points you in the right direction. I'm not 100% sure this is going to work, but I'm pretty sure what it's going to allow me to do is change this one of these tan squareds into secant squared minus 1, and then that's going to set up, hopefully, a chain rule. So let's see what happens here. So I'm going to go integral, leave this one alone. So just put that one back the way it is. Swap this out for its Pythagorean identity. Secant squared x minus 1. Still have your dx. Okay, let's see what we got now. So now I'm going to distribute that in there. And I've got the integral of tangent x squared, so u to a power, that times that, there's your du. So that's a nice integral that we can manage. I'll just put a dx on that. Minus, now it's this times this, which will be the integral of tan squared x dx. Well, that's not one of my differentiation rules. But if I basically just do what I did up here again, do it over again a second time, I should be in business. So this is going to be tangent x, so u to a power du. I don't want to touch this. This is perfect. This one, though, we're going to switch this out to its identity, secant squared x minus 1. And now that should be good too, because this is the derivative of tan, and the number 1 is easy to take the integral of. It's just an x. So we've now got a bunch of terms that we can anti-differentiate or take the integral for. So this becomes, add 1 to your exponent and divide by your, you have this pattern, u to the n du. This one is just one of your trig rules, and this one's just a regular number. So tangent cubed x over 3 minus tangent of x would give you that for its derivative. And then now you got to be careful that this minus goes into here, so it's really going to become plus x plus c. And one last one. So the giveaway here is that exponent being odd. And again, I'm not saying 100% of the time this is what you do, but very often, if you've got an odd exponent on one of your trig ratios, if you peel one off, what it does is it allows you then to play around with Pythagorean trig identities, because Pythagorean trig identities are based on ratios squared. So even if they're to the fourth or the sixth or something, you could raise them to exponents to get those. So this one, I'm going to go tan squared x secant to the fourth x tangent x dx. Tan squared is the derivative of secant let me see here. I'm not sure if this is going to work. So I could change this to secant squared minus 1, but that wouldn't really help. Oh, yeah, I should have. So I kind of get stuck here, which is good to show you what will happen. I'm kind of looking how this is all going to unfold, but it's not going to. I'm not going to get u to a power du's. What I should have done, I'm going to go back to the drawing board. I should have left this one alone. So here's a good example of that one or certain little percentage of the time where leave the odd one alone. And I should have split this into secant squared x dx. And you say, well, why would you do that? The reason I do that is because secant squared is the derivative of tangent. Well, I've got tangent. This could be the du. I'm going to swap this one out for the Pythagorean identity. So the question becomes tangent cubed x. Secant squared x is 1 plus tangent squared of x. Secant squared x dx. So now Both of these are going to multiply by each of these. And it's going to become the integral of tangent cubed x secant squared x dx, u to a power du sitting next to it, plus tangent cubed multiplied by tangent to the third is tangent to the fifth. You add the exponents when the bases are the same, and then you'd have to multiply by your secant squared from the other side. U to a power du. Perfect. Two chain laws. 1/4 tangent to the fourth x plus 1/6 tangent to the sixth x plus c. Okay, so that was a good example to show you how I kind of thought one thing might work. I got stuck, so I don't just give up. I just, well, what I'm doing doesn't appear to be helping me or working. I erase it and I start over and try something else. So, and you're always trying to set up, in my opinion, as often as possible, chain rules. U to a power du. So that whole notion of, hey, wait a second, why don't I get secant squared here isolated, and then that can serve as my du. When I split that in the original one, I split it to tan and tan squared, but if I should have thought more clearly about that, because neither tan or tan squared are derivatives of a trig function. So that wasn't really helping me set up chain rules. Versus splitting this one, it's helping me set up chain rules because one of the factors that I split it into can serve as your du. So hopefully that will point you in the right direction of how you're going to do integrals involving trig functions. So as you can see, they can get complicated. You do have to be competent in your trig identities. And whether you like it or not, when you jump yourself into science programs and courses that require you to do calculus at a university level, they just assume that you have mastered trig identities and that you're at your disposal. So they might not even go through those in the future. And just again, they would assume that you know all of those trig identities. So the more time and effort you put into working through these, the better off you're going to be. So I'm going to dig out some practice questions on integrals involving trigonometry. I'll put them in your notebooks, your digital notebooks, and I'll always try and make sure I find some with answers. Here's your one you got to watch for with answer keys, though. I showed you an example in the beginning that demonstrated if I do one strategy, another student does another strategy. There's nothing to say that they both won't work, which can also then generate answers that look very different. So if you're feeling confident that, I don't know, I think what I'm doing is okay, fire off a message and say, can you have a look at this question? Put it in your notebook somewhere where I can have a look at it, take a picture of it, whatever it is you want to do, and I can have a look at it and see if what you're doing is correct. All right, best of luck with these. And we've got a couple more little strategies left next week to get uncovered. And then we'll have lots of time then to get the practice part of this unit down.